Curious about AI but short on time? Want to cut through the jargon and understand the core concepts powering tools like ChatGPT and Bard? We're taking Google's Beginner AI course, originally condensed into a quick YouTube guide, and diving even deeper. Get ready to unpack artificial intelligence, machine learning, and deep learning without needing a technical background. Let's jump in. Welcome back to the Deep Dive. Today, we're tackling a source that aimed to simplify AI for beginners.
Right.
Specifically a YouTube video. It took Google's potentially quite lengthy AI course and basically boiled it down to about 10 minutes.
A quick summary.
Exactly. And our mission today is to go beyond even that fast-paced summary. We're going to pull out the essential knowledge you need, explore the relationships between these often confused terms.
Yeah, like ML, DL, AI.
And really solidify your understanding of the fundamental concepts in artificial intelligence.
And this source is great for that, I think. It provides a really clear, accessible framework.
Cuts through the buzzwords.
Yeah, it cuts through the noise around AI buzzwords and kind of gives us a map. It shows how terms like machine learning, deep learning, even large language models, how they all fit together.
Okay.
It directly tackles that common confusion and uses some simple analogies that really make these complex ideas stick.
And the creator of the video actually mentioned they were initially worried Google's full course might be too theoretical, maybe a bit abstract, but they found these foundational concepts were surprisingly practical. Like understanding them actually helped them use tools like ChatGPT and Google Bard more effectively.
Oh, interesting. So it wasn't just theory.
No, and it cleared up misconceptions they had. So what we're getting is this distilled, practical overview of foundational AI, straight from Google's own material, but filtered and clarified through this guide.
Sounds like a really valuable starting point for our deep dive today.
Definitely. So let's start right at the top. The source kicks off by defining AI itself. And it immediately presents this foundational structure, almost like nested boxes or a hierarchy. Where does it begin?
It starts right at the top with artificial intelligence, AI, as the broadest concept.
The big umbrella.
Exactly. It defines AI as a field of study focused on creating systems that can do tasks that, typically require human intelligence.
Okay.
And to make that relatable, the source uses a pretty helpful analogy. It compares the entire field of AI to physics.
Physics, like the whole science.
Yeah, the whole field. Physics is this huge scientific discipline, right? It covers everything from like fundamental forces, subatomic particles, all the way up to galaxies and the universe. It's enormous.
Right, lots of branches.
And AI is similar. It's this vast overarching discipline with loads of different approaches, theories, technologies, all aimed at replicating or mimicking intelligent behavior in machines. It's the big picture.
Okay, so AI is the massive umbrella, the whole field, like physics. Where does machine learning fit inside that huge scope?
So machine learning, or ML, that's presented as a really significant subfield within AI.
A
big piece. Sticking with the physics analogy, the source compares machine learning to, say, thermodynamics being a subfield of physics.
Okay, so specific branch.
Exactly. Thermodynamics focuses on heat, work, energy. Machine learning is a specific approach to achieving that broader AI goal. Its core idea is building systems that can learn from data.
Learning from data.
Yeah, instead of being explicitly programmed with step-by-step instructions for every single possibility, an ML system learns patterns and rules directly from the data it's given.
So it figures things out itself.
Pretty much. It adapts and improves over time without a human coding every single task. It's just one powerful way to build AI.
Got it. So AI is the big goal. ML is one key method to get there by learning from data. And then going down another layer, getting even more specific within machine learning, we find deep learning.
Exactly. Deep learning, or DL, is a further subset of machine learning.
Okay, so it's inside ML.
Yeah, right. All deep learning is machine learning. But not all machine learning is deep learning. It's a particular type of ML that uses specific structures, kind of inspired by the human brain.
Neural networks.
Yeah, what the source calls artificial neural networks. Think of it as a specialized technique within machine learning, especially good for complex data like images, audio, text, that sort of thing.
And then, getting even more granular, the source talks about different types of models that fall under deep learning. This is where we start seeing the tech powering the tools we use daily, right?
Yes, exactly. Deep learning models can be broadly categorized based on what they're designed to do with the data. The source highlights two main types: discriminative models and generative models.
Discriminative and generative.
And that distinction is really fundamental to understanding the output, the purpose of many modern AI systems. Are they deciding something or are they creating something?
And bringing it all the way down to the applications everyone's talking about now. ChatGPT, Google Bard. Where do they fit in this structure? Starts with AI, then ML, then deep learning, then these model types.
Okay, so large language models, LLMs, they fall under deep learning.
Right.
Specifically, they're a prominent type of deep learning model. And the tech that powers tools like ChatGPT and Google Bard sits right at the intersection of generative models and LLMs.
So they were generative models and LLMs.
Correct. They are large language models specifically designed to generate new content, mostly human-like text. They use that deep learning architecture to do their generative magic on massive text data sets.
Wow, okay. So just that structure itself is incredibly clarifying. Seeing AI as the whole field.
The big picture.
ML is the approach using data. DL is a specific type of ML using neural networks.
Yep.
And then different models like generative models, which LMs often are, sitting within DL. It really maps out the landscape, doesn't it?
It really does.
It makes it clear that when people just say AI, they might actually mean a specific piece within this much larger layered picture.
Absolutely. It takes that single, sometimes overwhelming term AI and just breaks it down into its component parts. Shows the relationship, the progression from the abstract goal to the specific techniques and models. Understanding this hierarchy is like the first step to making sense of all the rapid developments we're seeing.
Okay, with that high-level map in place, let's dig into machine learning a bit more. The source gives a really concise definition of its core process.
Yeah, at its heart, machine learning is described as a program that uses input data to train a model.
Train a model.
Right. And this model, once it's trained, it gains the ability to make predictions or decisions based on data it has never seen before.
So it learns from experience.
Exactly. The whole process is about learning from experience, the data, to generalize and perform tasks on new information.
And the source uses a really practical example here, doesn't it? To illustrate that idea of training and then using it on new data.
Yes, the Nike and Adidas example. They talk about training a model on extensive Nike sales data.
Okay.
Imagine feeding an algorithm years of historical sales records for Nike shoes. Details like design, materials, color, marketing budget, release date, price, sales figures. All of it.
A ton of data.
A ton. The model analyzes all this to learn the complex patterns. What seems to correlate with high or low sales for Nike shoes. It identifies which factors, or combination of factors, seem to be strong predictors of success.
So it learns what makes a Nike shoe sell well based on its past performance.
Precisely. Now here's where the prediction part comes in. The source says you can then take that same trained model, the one that learned the general principles of shoe sales from Nike's history,
Right.
and feed it data about a new shoe from Adidas.
Different brand.
Totally different brand. You give it the details of the new Adidas shoe price, style, marketing, release date, whatever, and the model uses the patterns it learned from Nike's data to predict how well that new Adidas shoe is likely to sell.
That's fascinating. So you're not retraining it just for Adidas. You're using the general patterns learned from Nike.
Exactly.
To predict something about Adidas.
It shows that these models aren't just memorizing the training data. They're learning underlying relationships. Principles that can be applied to new, unseen data from a similar domain,
That ability to generalize sounds key.
It's fundamental to the power of machine learning, taking insights learned in one context and applying them predictively in another.
The source then distinguishes between two of the most common fundamental types of machine learning based on the kind of data they use.
Right, supervised learning and unsupervised learning. And understanding the difference here is absolutely crucial. It dictates what kind of problems each type can solve, and importantly, what kind of data you need to train them.
Let's start with supervised learning. What's the defining feature there? How does it learn?
Okay, supervised models learn using labeled data.
Labeled data,
Meaning for every piece of data you feed the model during training, you also provide the correct answer or the category it belongs to the label. It's like flashcards, maybe. Data on one side, answer on the other.
Okay.
The source uses a clear example with restaurant data, looking at tips.
Right, plotting the bill amount against the tip amount.
And the key for supervised learning is that this data is labeled. For instance, a blue dot on their plot might mean the order was picked up by the customer.
Okay.
And a yellow dot means it was delivered. So a $50 bill with an $8 tip might be labeled pickup, blue. A $75 bill with a $12 tip labeled delivered, Yellow.
So the model sees the inputs and the correct output label.
Exactly. Bill amount, tip amount, and the type of order. It learns the relationship between the bill, the order type, the label, and the tip that resulted.
And with that labeled history, how does it predict for a new order then?
Well, once it's trained on that labeled history, if a new order comes in, say, a $60 bill marked as delivered, a new yellow dot, the model uses the patterns it learned specifically from all the past delivered orders to predict the most likely tip for this new $60 delivered order.
So it uses the delivered pattern it learned.
Right. It's learning a direct mapping from the input features, bill, order type, to the target output tip based on the correct examples it saw. The supervision comes from having those correct labels.
That makes sense. You're supervising its learning by showing it the right answers.
Yeah.
So how does unsupervised learning differ? What data does it use?
Unsupervised models look at unlabeled data.
No labels at all?
None. No predefined categories, no correct answers given during training. You just give the model raw data, and its job is to find inherent structure, natural groupings, or patterns within that data, all by itself.
Okay, so it's finding patterns without being told what to look for.
Exactly. It's not trying to predict a specific outcome based on labels. It's trying to understand the organization, the relationships that already exist in the data.
The source used employee data as an example for this one, right? Tenure and income.
Yeah, plotting employee tenure at a company against their income. If you just plot those 2 points for thousands of employees without any other labels.
Just the dots.
Just the dots. An unsupervised model can look at that distribution and identify clusters, where data points naturally group together.
Like groups of employees.
It might find a group with short tenure but high income, another with longer tenure and maybe more moderate income, a third with long tenure and very high income. It sees these clumps in the data.
And critically, this data is unlabeled. You're not telling the model, these are engineers or these are managers.
Exactly. The model doesn't know what those groups represent in a business sense. It just sees that the data points cluster distinctly based on tenure and income.
So how is that useful?
Well, by identifying these natural clusters, you can then use the model to solve a related problem. The source gives the example of asking, if a new employee joins with X years tenure and Y income, do they fall into the group that looks like it's on a fast track?
And the model could figure that out based on which cluster the new employee's data point is closest to.
Precisely. It uses the inherent structure it discovered to assign the new employee to a category it identified, even though you never explicitly defined or labeled that category beforehand. It's finding structure, not predicting a predefined outcome.
The source gives a pro tip about another really fundamental difference between supervised and unsupervised, related to how they refine themselves, how they learn.
Yeah, this is a really key distinction about the feedback loop. With a supervised model, after it makes a prediction, say, it predicts a $10 tip for that $60 delivered order.
Okay.
You eventually find out the actual tip received. Maybe it was $11.50.
Right, you get the real answer.
So the model can compare its prediction, $10, to the actual outcome, $11.50. Because it has that ground truth from its labeled training data and sees the actual results for new data, it can identify the error, the gap.
Yeah, and fix itself.
It uses that difference to adjust its internal workings, its parameters, and improve its accuracy over time. It's basically learning from its mistakes relative to the correct answer provided by the labels.
So supervised learning has this built-in way to check its work against the answer key and get better.
Exactly. It's got a teacher, essentially. Unsupervised models, though, lack that labeled truth to compare against.
Right, no answer key.
They just identify patterns and structure. They don't have a target value or category to aim for or a right answer to compare their findings against. So they don't have that feedback loop that corrects predictions based on a known desired outcome.
So they can't really improve their predictions in the same way.
They can tell you how data points group together, but they can't tell you if that grouping leads to a correct prediction, like a supervised model predicting a tip amount or classifying an image. That's why supervised is for prediction and classification, where you have labels, and unsupervised is more for clustering, finding anomalies, simplifying data where you're looking for structure.
Understanding that feedback loop difference really highlights their different purposes, doesn't it?
Yeah.
Supervised needs that often expensive labeled data because it needs the answer key. Unsupervised can find insights in raw data because it's just looking for the inherent structure. Okay, we've explored machine learning basics, supervised versus unsupervised. Now let's delve deeper into deep learning, which we know is a specific type of ML using those artificial neural networks.
Right. Deep learning is defined by its use of artificial neural networks. The source wisely suggests, maybe don't get totally bogged down in the super complex math of how they work initially.
Probably good advice.
Yeah, but it gives us the essential conceptual idea.
And what is that core concept? What are these neural networks supposed to mimic?
They are computational structures inspired by the biological neural networks in our brains.
Okay, brain-inspired.
The source describes them as having layers of nodes and neurons, kind of interconnected like a web. Each node or neuron in one layer processes some information and passes it on to the next layer. Data flows through these layers, getting transformed at each step.
And the deep part of deep learning that comes from the number of these layers, right?
Precisely. A key point mentioned is that the more layers a neural network has, the more complex patterns and representations it can potentially learn from the data.
More layers, more power.
Kind of. A network with just a few layers might learn simple things like edges or corners in an image. But a deep network with many layers can build on those simple features from earlier layers to recognize much more complex concepts in the later layers, like shapes, textures, eventually whole objects or faces.
Building complexity layer by layer.
Exactly. That ability to automatically learn these hierarchical representations from raw data is a huge part of deep learning's power.
And the presence and power of these layered networks allow for different ways of learning, maybe blending supervised and unsupervised, which the source brings up next.
Yes, deep learning models are particularly good at something called semi-supervised learning.
Semi-supervised, a myth.
Yeah, it's a very practical hybrid approach, often used in the real world where getting tons of label data is just hard or really expensive.
So how does semi-supervised learning work? How does it blend the two?
Okay, in semi-supervised learning, a deep learning model gets trained using a combination, a small amount of labeled data.
The expensive stuff.
Right. Alongside a very large amount of unlabeled data. So you have some examples where you know the answer and a huge pool of data where you don't.
Got it.
And the power of deep learning's neural network structure lets it effectively leverage that small bit of labeled data for initial guidance, and then apply what it learned to the massive unlabeled data set to discover broader patterns.
So it's not all labeled like supervised or all unlabeled like unsupervised. It's in the middle, using the labels it does have strategically.
Exactly. It's super valuable when labeling data takes a lot of human effort or expertise or cost, which is true in many fields.
The source gives a great tangible example of this hybrid approach in action: bank fraud detection.
Yeah, perfect example. Imagine a big bank processing millions, maybe billions of transactions daily.
Wow.
Training a purely supervised model for fraud detection would ideally mean manually reviewing and labeling every single transaction as legitimate or fraudulent.
Impossible.
Totally impossible. The volume is just too high, and you'd need an army of analysts. So the bank might only be able to manually review and confidently label a tiny fraction, say 5%, of their transactions as either verified fraud or verified legitimate.
So 95% are just transactions, unknown.
Right, just unlabeled. Now, a deep learning model using a semi-supervised approach can be trained here. It first uses that small 5% of carefully labeled data.
Okay, the known examples.
From those verified examples, the model starts to learn the characteristics, the patterns linked to fraudulent transactions. It learns what features amount, location, timing, account history seem to indicate fraud, based on the few examples it knows are definitely fraudulent.
So it gets an initial, maybe limited understanding from the labeled bits.
Yes, it learns the signature of fraud from those few examples. Then the magic, as the source calls it, happens. It applies that learning and uses its ability to find complex patterns in the massive 95% of unlabeled transaction data.
It looks for similar patterns in the big unlabeled pool.
Exactly. It looks for transactions in that unlabeled pool that show features similar to the fraudulent patterns it learned from the labeled set. By combining the guidance from the small labeled set with the pattern finding on the large unlabeled set, the model gets much better at spotting potentially fraudulent transactions within that vast unverified pool.
Better than it could with just the 5% labeled or just the 95% unlabeled alone.
Much better. It leverages both. And this improved understanding helps it make better predictions for future incoming transactions.
So it can flag suspicious new transactions more accurately.
Precisely. It makes the fraud detection system way more effective than if it only used the tiny labeled data set for supervised training, or just used unsupervised methods on the raw data without any initial guidance. It gets the best of both worlds to scale up accurate prediction using limited labeled resources.
That example really clarifies the power and efficiency of deep learning with semi-supervised methods. It can get significant value from data sets where full labeling just isn't practical.
It's a key reason deep learning has become so huge in areas dealing with massive amounts of data, where getting labels is a major bottleneck.
Okay, so deep learning uses neural networks. Can use semi-supervised learning. Now, the source divides deep learning models themselves into two fundamental types based on their output or purpose.
Right. Discriminative models and generative models. This is a core distinction for understanding what an AI system is fundamentally designed to do.
Decision versus creation.
Exactly. Are you giving it data and asking it to make a decision about it, or are you giving it input and asking it to create something new based on that data?
Let's start with discriminative models. What's their main job?
Discriminative models are primarily focused on classification, sorting things.
Okay.
They learn from the relationship between data points and their labels to basically draw a boundary or discriminate between different categories. Their output is usually a label, a category assignment, maybe a number, or a probability indicating how likely a data point belongs to a certain class.
Good for sorting, filtering, making decisions.
Exactly, based on learned distinctions.
The source uses the classic cat versus dog example here, right?
Yes. Imagine you have a big collection of images. For a discriminative model, you would painstakingly label thousands of these images as either cat or dog.
Explicit labels again.
Explicitly telling the model, this picture is a cat, this one's a dog. The model learns the features, the visual patterns that discriminate cats from dogs based on these labeled examples. It learns what makes a picture a cat versus a dog by analyzing the examples where you've provided the right answer.
And then if you show it a new picture it hasn't seen before.
If you show the trained discriminative model a new image of, say, a dog, it analyzes the image, compares its features to the patterns it learned, and predicts the label for that new picture. Its output will be dog.
Or maybe a probability like 95% dog.
Exactly. Its task is to assign the correct category label to the new data point based on its training. It's not creating an image, it's making a classification decision about an existing image.
Okay, so how are generative models fundamentally different in their purpose and output?
Unlike discriminative models that classify existing data, generative models learn about the underlying distribution and patterns within the training data itself.
The patterns in the data.
Yeah. Their goal is to understand how the data is structured so that they can generate entirely new examples that resemble the original data.
Create new stuff.
Exactly. After getting some input, often a text prompt, they create something basically from scratch based on the patterns they learned. They are creative content generators.
So going back to the animal example, but for a generative model,
Yeah.
how would that work differently?
Okay. With a generative model in this case, you might train it on a large data set of animal pictures, but maybe you don't explicitly label every single picture cat or dog.
List labeling, or maybe none.
Could be. The model analyzes the visual patterns across all the images. It learns the typical structures, textures, colors, combinations of features that appear frequently. It might learn that one cluster of patterns corresponds to creatures with pointy ears, whiskers, certain body shape.
Cat-like features.
Right. And another cluster corresponds to floppy ears, different snout, different body structure.
Dog-like features.
Exactly. It learns the characteristics that define these different types of animals just by looking at lots of examples.
So it learns the essence or distribution of catness and dogness from the raw image data itself.
Pretty much. It learns the statistical properties, the pixel relationships that make up cats and dogs. So when you then give it a text prompt like generate an image of a dog, it uses its learned understanding of what a dog looks like based on the patterns it found to create a brand new image of a dog that didn't exist before. It's not finding an existing picture and labeling it. It's synthesizing a new visual based on the patterns it learned.
The source gives a really simple, practical way to quickly tell if an AI system you're using is generative AI or not. A rule of thumb.
Yeah, this is a great little tip from the source. Basically, if the output you get from the AI is just a single number or a simple classification like spam, not spam, fraud, not fraud.
Or like a probability score.
Right, or a probability score like 80% chance of rain. Then, according to this source, it is not generative AI.
Okay.
Those are typical outputs of discriminative models or other kinds of analytical AI.
So if the output is a decision, a prediction value, or a category, probably not generative?
Correct. It is generative AI when the output is something more complex, something that is a newly created instance resembling the training data.
Wow.
The source says this includes natural language text, speech, an image, audio, even code. Basically, if the AI is producing new samples of content similar to the data it was trained on.
writing text like text it read, generating images like images it saw.
Exactly. Then you are likely dealing with generative AI.
That distinction is super helpful. It clarifies that generative AI isn't just about analyzing data. It's about using that analysis to actually build or create something novel.
Right. It isolates that creative content-producing aspect that distinguishes tools like ChatGPT or Midjourney from, say, a spam filter or a credit score predictor.
Okay, so generative AI is all about creating new content, new samples of data. The source breaks down several common types of generative AI models, often distinguished by the kind of content they generate, usually triggered by text input.
Yeah, the core function is generating new samples based on learned data patterns, and the input, often text, guides that creation.
The first type is probably the most widespread and familiar right now.
Absolutely. Text-to-text models. You give it text input, a question, a command, a topic, and the model generates text as output.
Like ChatGPT, Bard.
Exactly. The source highlights ChatGPT and Google Bard as prime examples. They're trained on massive data sets of text and code, learning grammar, facts, reasoning, different writing styles, so they can produce coherent, relevant, human-like text for a huge range of prompts.
Moving beyond just language, there are models that translate text instructions into visuals.
Right, text-to-image models. You give them a text description, a creative prompt detailing a scene, style, subject, and they generate an image matching that description.
Midjourney, D-Lee.
Yep. The source mentions Midjourney, D-Lee, Stable Diffusion. And they note these models can also edit existing images based on text commands. So you get flexible creative control using natural language. They've learned the link between words and visual concepts from huge image text data sets.
And taking that to the next level. Moving pictures.
Text-to-video models. They take text prompts and generate or edit video sequences. Not just one frame, but a whole series forming a clip.
That feels moving fast.
It really is. The source mentions examples like Google's Imagen Video, Cog Video, Make Video, shows generative AI isn't limited to static images. They learn how things move and change over time from video data and text descriptions.
There are even generative models for creating assets in 3D.
Yeah, text-to-3D models. You describe a 3D object in text, and the model tries to generate a 3D mesh or representation. Super useful for game development, VR, design, where making 3D assets is time-consuming.
Any examples?
The source mentions OpenAI's Shape-E model. They learn the connection between text descriptions and 3D shapes from datasets of 3D models and text.
Okay, this last type mentioned by the source feels a bit different from creating media like text or images. Text-to-task.
It is a bit different. Text-to-task models are trained to understand a text prompt and then perform a specific action or task in the real or digital world. They don't just generate content.
They do something.
Yeah. They translate natural language instructions into executable commands that interact with other systems.
And the example the source uses makes this very clear.
They use the example of typing Gmail summarize my unread emails into a tool like Google Bard.
Okay.
In this case, you're not asking Bard to write about your emails or draw your inbox. You're giving it a natural language command that triggers an action. Accessing your Gmail with permission, finding unread emails, analyzing them, and generating a summary for you.
So the model links the words to an action, like calling an API.
Exactly. It's trained not just on language, but on how language corresponds to specific actions.
This type shows generative AI is moving beyond just creative stuff into becoming like an interface for automating actions based on how we naturally speak or type, generating action from text.
Yeah, it points towards AI becoming a more intuitive way to command our digital tools.
The source circles back to large language models, LLMs. Reminds us they're a subset of deep learning, but then highlights a key characteristic and training process that distinguishes them, especially in how they're deployed.
Yes, while many big generative AI apps are LLMs, the concept of an LLM itself really emphasizes scale and a specific training method. The defining characteristic of LLMs is that they are typically pre-trained on absolutely massive, diverse data sets.
Pre-trained. What does that mean exactly?
It means they go through this initial, incredibly computationally expensive training phase on a huge amount of data, like vast swaths of the internet, digitized books, code, and more.
Wow.
And this pre-training is done without a specific task in mind. It lets the model learn grammar, facts, reasoning, common sense, world knowledge, just from the patterns in all of that data.
Like giving it a general education.
Exactly, a comprehensive general education in language and information.
So they get this broad foundational understanding first, and after that, huge initial training.
After pre-training, these general-purpose LLMs are usually fine-tuned for specific tasks or domains.
Fine-tuned.
Yeah, this involves training the pre-trained model further, but on a much smaller task-specific data set. This fine-tuning specializes the model, makes it really good at a narrower set of tasks like translation, summarization, answering questions in a specific field, or writing in a particular style.
So it builds on the general knowledge to become an expert.
Exactly. The fine-tuning builds upon the broad capabilities learned during pre-training, making the model an expert in a specific area.
The source uses a simple, memorable analogy to explain this two-step process. Pre-training, then fine-tuning. The dog analogy.
Yeah, the dog analogy is great. Imagine you get a young pet dog. It gets basic pre-training, learning fundamental commands like sit, come, stay.
General obedience.
Right. It learns how to be a generally well-behaved companion. That's like the LLM pre-training, giving it broad general skills.
Okay, that's the general education part.
But if that same dog is going to become a specialist, like a police dog trained to detect substances, or a guide dog helping someone blind, or a hunting dog.
Needs more specific skills.
Exactly. It receives specific intensive training tailored only for that demanding job. It's fine-tuned for that specialist role. It builds on its basic obedience, but gets a whole new set of highly specific skills for that one task.
So the pre-trained LLM is the generally capable dog, and fine-tuning turns it into the specialist police dog or guide dog, focusing its power on a particular area.
Precisely. The heavy lifting of learning general language patterns is done in pre-training. The nuance and expertise for a specific application come from fine-tuning.
The source provides a really compelling real-world application of this pre-training fine-tuning model. In a hospital.
Right. A hospital might want to use AI to help doctors diagnose conditions from medical images or analyze patient records.
Complex stuff.
Very. Building a powerful LLM from scratch that understands complex medical language would be astronomically expensive. Needs huge computing power, specialized AI expertise. Most hospitals just don't have that.
So what do they do instead?
They can leverage the pre-training done by a large tech company. A big tech firm might develop a general-purpose LLM trained on massive data, maybe including some public medical literature.
Okay.
The hospital can then license or use this pre-trained general LLM. But here's the key. The hospital then fine-tunes that general model using its own first-party medical data.
Their own data, like patient records.
Yeah, anonymized patient histories, internal diagnostic reports from their own doctors, notes on treatments and outcomes within that hospital, maybe large archives of their medical images linked to diagnoses. Their unique stuff.
They use their unique proprietary data to make the general model an expert in their specific medical context.
Exactly. By fine-tuning the general model with their highly specific, domain-relevant medical data, the LLM becomes incredibly accurate and useful for tasks within that hospital.
Like helping with diagnosis.
Assisting with differential diagnoses, identifying patterns in patient outcomes, summarizing complex medical histories, analyzing radiology reports to flag potential issues with maybe greater precision. The model learns the specific terminology, nuances, diagnostic patterns common in that hospital's practice.
The source frames this whole approach, big companies pre-training smaller institutions fine-tuning, as a win-win scenario. Why?
Well, it's a win for the large tech companies because they invest billions developing these foundational, powerful, general-purpose LLMs. They create this core infrastructure.
And then they can sell access.
Right, offer access to these models as a service.
And it's a win for all sorts of other organizations, too.
Yes. Institutions and companies in different sectors, healthcare, finance, retail, law, manufacturing. They might lack the resources to build an LLM from scratch, but they do often possess incredibly valuable, unique, domain-specific data sets.
Their internal data is their edge.
It's their competitive advantage. They can use this proprietary data to fine-tune the pre-trained general models from the tech companies. This lets them unlock advanced AI capabilities tailored to their specific business needs using their unique data without the huge cost and effort of creating the base model themselves.
So this model really speeds up the application of advanced AI across different industries. It separates the massive R&D for the foundation from the specialized knowledge needed to make AI useful in a specific field.
It basically democratizes access to highly advanced AI capabilities. It allows companies with domain expertise in data, but maybe not huge AI research labs, to build powerful, specialized applications.
Wow. We've gone from the very top of the AI hierarchy through machine learning, deep learning, the types of models like discriminative and generative, and finally drill down into large language models and that critical process of pre-training and fine-tuning that makes them so adaptable. This breakdown, drawn from our source material, provides such a clear map of this really complex and fast-moving field.
Yeah, understanding the structure of these core concepts, it helps you move beyond just hearing the buzzwords, you know? You can appreciate what different AI tools are designed to do. Are they sorting or are they creating?
Yeah.
And get insight into how they might have been trained, why they have certain capabilities. It just makes evaluating and using AI tools much more informed.
Whether you're using a creative generator like Midjourney, getting help writing an email from ChatGPT, seeing AI suggest products on a retail site, or maybe encountering it in a professional setting like analyzing financial data, or, like we discussed, aiding in medical diagnostics. This foundational knowledge gives you a framework. It helps you see the underlying mechanics and recognize which type of AI is likely at work and why.
And it clarifies why tools like ChatGPT and Bard got so much better, right? As their underlying models got bigger, had more extensive pre-training, better fine-tuning methods.
Right.
It also explains how those domain-specific AI applications, the ones that are incredibly good at just one thing, like medical analysis or legal document review, are built. By combining powerful general models with that highly specialized, often proprietary data, considering this win-win scenario the source described, where creating the powerful general AI foundations is concentrated in large companies, but the specialization happens when those models are fine-tuned by domain experts with their unique data. It does raise an interesting question for you to think about.
Okay.
What are the potential benefits of this model? Accelerating innovation, solving super specific problems across industries sounds great. But what are the potential challenges or risks when the core AI infrastructure is maybe held by just a few powerful players, even if the specialization is decentralized?
Good question.
As AI gets integrated into more niche areas using proprietary data, what unique problems become solvable? And what new dynamics of power, access, or even bias might emerge from this kind of structure? It's definitely a key tension in the current AI landscape to keep an eye on.
Well, this deep dive into the fundamental concepts of Google's AI course, as distilled and clarified by our source video, provides a really solid understanding of modern artificial intelligence, I think.
Yeah, it underscores the interconnectedness of the field and the crucial roles of both that foundational research and the tailored application.
We really hope this deep dive has helped clear up some confusion and maybe sparked your curiosity to learn even more about AI. If you found this deep dive valuable and want to continue exploring complex topics with us, you can find more like it on the podcast affiliate. We're working towards a goal, so if you enjoy what we do and want to support future deep dives, please help us reach 1,000 subscribers. Your support really does make a big difference.
Thank you for joining us for this exploration. We'll be back with another deep dive soon.